My name is Amir Rawdat. I'm a TME at NGINX. I've been working at NGINX for about 1.5 years now. And a lot of what I do is performance tuning on open source technologies, mainly NGINX. And today we're going to go over 4 performance tips that you could use today in your testbed to maximize performance with NGINX. So let's get started. So we're going to talk about the multi-process architecture with the QPI bus. So this is the web server topology that we used in testing NGINX as a web server. So we have a client machine generating traffic using WRK, directing that traffic to a web server running NGINX. Pretty straightforward. It's running 240 GBE QSFP plus NIC cards. And this is the reverse proxy topology that we used. Same idea. Now we have 3 machines and running NGINX as a reverse proxy doing SSL termination. And we are running NGINX on the web server as well, but we are not running SSL. So just to go over the tech specs, so the client machine has 2 sockets, 22 cores per socket, 2 threads per core, 128 gigs of RAM running Ubuntu Xenial, and the reverse proxy and web server is almost the same, but we have 24 cores per socket instead of 22. And the clock speed is a little faster. But anyway, that is the tech specs. So considering that this...
One quick question for you. What is the make or model of the NIC that you test with?
Sorry?
What make or model of the network card did you use to test with?
It's Intel.
Okay.
Intel, yeah. All right, let's continue. So this is considering that, goddamn, can't even see. Anyways, do you have a, yeah, thank you. I'm gonna need the pointer. Thank you. Okay, so considering that this machine is our reverse proxy web server, right? There is my 2 sockets, 24 cores in each socket, 2 threads per core, each having a local RAM and directly connected to a NIC card, right? So one very important note is if we want to maximize performance, we want to minimize using this QPI bus. So if I'm serving a static file and I'm executing a memory reference instruction from this CPU node, I want to access it from this memory block and not going through the QPI bus to the remote memory block. Also, if I'm getting an incoming connection from this NIC card, I want the CPU node connected to it to run the interrupt service routine for that incoming connection. Why? Because this guy is slow. QPI bus is slow. So, that being said, the first performance tip, duplicate NGINX configurations. So, like, what does that mean, right? Okay, so what does it mean? We're going to create 2 NGINX instances, right? And forget containers, forget VMs. We're talking bare metal here. 2 NGINX instances with their separate master processes spawning their own worker processes, 1 bound to CPU node 0 and 1 bound to CPU node 1. And the way we do that is by enabling worker CPU affinity, which means binding worker processes to CPUs. This is the NGINX configuration of the first instance. I have 48 worker processes because I have 24 cores and 48 threads per socket. Over here, I'm binding the first 24 cores from right to left on CPU node 0, and the remainder 24 virtual cores on CPU node 0 as well. And that is how we bind it to CPU node 0. Also, worker rlimit no file. It's a directive to set the limit of open file, the maximum numbers of simultaneous open file descriptors that NGINX can use. So here we set it to a high number, and depending if you're using NGINX as a reverse proxy or a web server, if you're using as a reverse proxy, you will have more open file descriptors open because you have to take into account the client connection and the upstream. Whereas with just a web server, it's just the client. So, instance 1. Now, instance 2 is almost the same thing, but now the bits are inverted. Because now we have the second instance, and we're binding it to CPU node 1, which is the 24 cores on node 1, and then the remainder of virtual cores on node 1. Now, deploying these instances is really, really easy. All you have to do is, on the command line, you type in the NGINX binary, the C flag, and the path to the configuration instance 1, we just went over, and then NGINX C flag, path to configuration instance 2. And then once you enter those two, that's it. So to check that it's working, you run a ps this command, and you should see, so because we had like 48 worker processes, you're going to see one master process and then 48 of these, and then another master process and another 48. That's how you know it's working. And if you want to kill it, you just do pkill nginx. So that's the first performance tuning tip. So let's go to the second one. Additional configuration directives. So one big thing, if you want to increase performance, is disable logs. If you don't care about logs and you care more about performance, then disable logs. You'll get better performance. Another thing, keep alive timeout. You could set a timeout for a client keep alive connection to stay alive. This case, we set it to 315 seconds. Now, also, for each keep alive connection, you can set the maximum number of requests that can be served in that keep alive client connection. Here is 10 million. Send file on, that tells NGINX to copy data between file descriptors at the kernel level. So if you have a file descriptor at a socket, and then you have a file descriptor from an application, it will copy it at the kernel level. So it's faster. And now, if you're sending that data outbound and you prepend a header to that data, TCP no push on means do not send partial TCP frames. Send to maximize the throughput utilization and the payload TCP frame size. So do not send partial TCP frame. That's what TCP no push is. And no delay basically means send it out as fast as possible. So if you do have a partial TCP frame in the buffer and it's been there for long, it's going to send it out anyway, regardless of whether you enable that or not. So that's that for HTTP context. Now this is where it gets really interesting. Over here, I'm listening on, in the virtual server, I'm listening on a socket that needs to be directly connected to CPU node 0, because we binded those worker processes to CPU node 0. To avoid using the QPI bus, we need to make sure that it's connected to CPU node 0. And reuse port is something you want to use if you have a multi-process environment. It will help in performance in a multi-process environment, because what this will do is it will bind multiple sockets to one port. So you will have multiple socket listeners, each assigned to a worker process, as opposed to have only one socket listener and then multiple worker processes reaching out to that one socket listener. The only downside to this is if you have a worker process and it's blocked by a connection, not only will that connection be blocked, but all the other connections that got assigned to that worker process by the kernel. So by default, you will have multiple processes reaching out. But in this case, that's where the only problem would be. So test it out, doesn't hurt to test things out. So there you go. And this is the file directory that we're serving, root bin. Okay, moving on. Exactly the same thing on instance 2. Now we're listening on a different socket directly connected to CPU node 1. That's the only difference. So next, that was the web server config. Now reverse proxy, kind of similar. We defined our socket here. Everything is cool, except now we have a location context, and we set the proxy HTTP version to 1.1, which is the recommended protocol for keep alive connections to the upstream. And we set the connection header to blank because we're doing SSL termination. And then we go ahead and proxy that connection to upstream web server. And we set a cache for the keep alive connections to the upstream servers. So that's the config for the reverse proxy. And another thing you might want to note is this is 10.10.11. The next one is different because on the web server, we also have two sockets, NGINX, CPU node 0, CPU node 1, right? So we're proxying to two different upstreams on each instance. Okay, so that's instance 2. Oh, what is that? So, can anyone tell me why we're getting this? Sorry? It starts with a Q. There you go. Yeah, QPI bus. So, what's happening is NGINX instance 1 bound to CPU node 0 is getting the file, is caching in its memory, but it's not replicating it to CPU node 1. So CPU node 1 has to go through the QPI bus and go to the local memory to fetch the file. Now, the more worker processes we use from CPU node 1, which is the remote CPU, the more latency we're going to have because we're going to be using the QPI bus more. And the QPI bus sucks. So. So they're at 100%.
Oh, they're all 100%.
Yeah, 100%. Yeah, they're at 100%. I run HTOP all the time. I see all the greens and the reds and all that stuff. It's pretty cool. Anyways. So the simple solution is to simply just duplicate the file, change the directory on the second instance. So this is the same. The second instance, I just change it to another directory. That way, each instance will have their own cached file locally. So if you just do that, you get this. So much nicer flow here. Over 2 million requests per second for 1 KB file size, 94,000 requests per second for 100 KB file size, and 9 to 10,000 for 1 megabyte file size. Reverse proxy testing. Oh, I didn't explain the graph, sorry. So this is a web server test, by the way. This is, yeah, so number of cores. Hyper-threading is enabled, right? So I'm using both threads per core. So 24 cores, 48 threads. This is the same thing, but reverse proxy testing with, so requests per second, hyper-threading enabled, requests per second here, number of cores here. Just under 2 million requests per second, so it's kind of expected. As reverse proxy, the number is just a little lower. So there you have it. Interestingly enough, this does not have the same effect on connections per second. So when I was testing it for connections per second, when I actually terminate the connection every time, you don't get this significant increase in performance when you separate the files. Just something to pick your brain. Did I skip? Okay. So this one is like the least interesting one. It's like because it didn't help me much in performance, but I'm going to go over it anyway because I'm just going to give you my recommendations. So one thing you might want to do is increase or set the minimum, default, and max size of the received TCP buffer in bytes and set the write buffer. So this is the receive, this is the write buffer, TCP in bytes to mitigate dropping packets in high load networks. So if you're getting a really, really high load of TCP packets, you might want to set that. Another thing you could do is increase the size of the processor queues. So when you're getting incoming connections and you're not fully utilizing all the CPU queues. Some of them are overloaded. So you might want to mitigate dropping incoming connections, so you can go ahead and set them to a bigger number. Here's 250,000. And finally, this guy, so it's not just TCP. So this is the operating system receive buffer and the operating system write buffer, max and bytes, not just TCP. So whether it's TCP, UDP, it's OS. Okay, that's so that was in my test, and it didn't really increase performance for me, but I just said it anyway. It could, in really high load networks, it could.
Is there another thing I was just going to ask about the backlog? You had that backlog in the other one.
All right, yeah. So in the NGINX config, and then this one.
So why is it that we have to set it in both places? Why can't
You don't have to. It's kind of redundant.
oh, really?
Yeah. It's redundant. You don't have to. I just put it in there for show, but it doesn't really help. Yeah. So you can choose. I would set it on the NGINX, not on the OS.
Yeah, that's what I noticed. That
Yeah.
the next one is it overrides or takes
Right.
precedence over this one.
Right. So yeah, I would use the NGINX directive. But anyway, next one, disabling TCP timestamps. So timestamps are TCP time extensions that are used for like round trip time measurements and protect against wrap sequence to avoid data corruption, right? So that being said, you may not want to disable it, but it could help in performance. So test it out yourself and see how it works. And you'll see why in the next slide how it helps performance, by the way. If you want, so these two did not help in performance when I tested it out. They could theoretically help you, but for me it did not help. So if you want to set a broader range of ports so that you have more open ports on the client side, therefore you have more open client connections, right? Which will theoretically give you more performance. And whenever you have a TCP connection, on one endpoint, you always have someone doing a time wait in the time wait state, which is at the end of the connection when it's about to get terminated. You could reuse that time wait state to reestablish an outgoing connection, which could help you reestablish connections faster. But these two did not help for me. So consider using them at your own risk. So timestamps helped. This is a NGINX web server test for requests per second serving a 1 megabyte file size. Number of cores here, requests per second here. Disabling timestamps, I get a higher peak at 36 cores. Hyperthreading is disabled here. Over here, 36 cores, so we get a higher peak, basically.
Why the number is 16 and 24? That doesn't make sense. The performance is worse when the timestamp is disabled.
I did the testing and I just cared about the peak, higher peak. That's what I looked at in terms of that. So it's what I'm trying to communicate to you guys is this, the peak. Okay, yeah. All right. Which leads us to our last performance tip, receive side scaling and transmit packet steering. So every network interface has interrupt request lines. What we want to do is we want to bind those interrupt request lines to the CPU node that is directly connected to that network interface. And the way we do that is we're going to use receive side scaling and transmit packet steering. So there's a Linux daemon that balances it out for you, but we want to set it manually. We want to set it manually so that we can bind all the interrupt request lines from this interface name to a node. So what we do is we turn off IRQ balance. You go to this GitHub repo, clone it, you run this script, and what it's going to do is going to take the interrupt request lines from this interface and bind it to the CPU node. So here it'd be 0 and nickname, and then 1 nickname. And then, so it's IRQ affinity. CPU affinity, IRQ affinity. So we're binding interrupts to CPUs. So that's the receive side scaling end. So we also have the transmit packet steering end, which is the part where, oh, now I want to send something, so interrupt service routine. So what CPU are we going to run for the interrupt service routine when we're transmitting packets? So you can go ahead and set this command with this interface name. So what you end up having is a one-to-one receive side scaling, and so the receive queue and the transmit queue both bound to the same CPU to avoid running other interrupt service routine on other CPUs.
There's no bonding on the NICs like that, right?
Sorry?
There's no bonding on the NICs at all. When you are setting up this way, they are separate NICs, they are not bonded.
They're separate NICs, yes. And so if you want to maximize performance, back to performance, we want to assign each interrupt request line to a CPU, and one CPU only. But in my case, I had more IRQs than I had CPUs. So I assigned 2 IRQs to one CPU queue. I didn't have a choice. I'm still maximizing my performance. So do what you can with it, basically. That's that. So no graphs this time. This is a table. Change it up a bit. Receive side scaling and transmit packet steering is disabled. We got 2 NGINX instances, one bound to CPU node 0, one bound to CPU node 1. Hyperthreading is enabled, testing connections per second. We get these numbers. Now apples to apples comparison, just enable receive side scaling. So take note here, 41,000, 35. When we enable it, everything's higher. So there's that. This is just numbers to back it up. So putting everything we just talked about together, this is testing NGINX as a reverse proxy, connections per second, hyperthreading enabled with RSA 2K. We get 44,000 connections per second for 1 KB and just under 40,000 for 100 KB.
You have the non-optimized view that we can do like comparison against.
Do you mean the one where you just don't do anything?
Yeah.
No. You mean like before and after?
Yeah.
No. Just the optimized one. Okay, so.
Can I ask a question about that?
Sure.
So from 1K to 100K, that's a 100x
Right.
size. But from 100K to 1 meg, that's much less. But the drop is significant. Any way to sort of explain that performance difference in terms of what is going on?
You mean because the drop is significant?
Yeah.
Well, it's supposed to be significant.
No, because from 1 to 100 and 100 to 1,000, the factor in terms of the size itself is so much.
So it's,
That's why I'm asking that question. I would have expected the red to be even lower and then subsequently the yellow, right? But here it shows that from 1 to 100 it's not as much, but from 100 to 1 megabyte, there seems to be some threshold that if you cross, it significantly reduces performance.
right, so it has something to do with the queue size, the processor queue size. Something about how connections just, get enqueued to the queue, and then there's just a bottleneck there, or a throughput bottleneck too. So with a larger request size, you get a higher throughput. So there could be like a throughput bottleneck. Yeah. All right. Anybody heard of QuickAssist? Okay. So QuickAssist is a hardware accelerator developed by Intel. We use it with NGINX to offload cryptography and to accelerate SSL transactions. And we did performance testing with QuickAssist, just some initial testing, and we saw some significant improvements. So we're just, we're working with Intel. We're Still validating the numbers. It's not set in stone yet, but I did testing with it, and we got some pretty significant performance improvements. And here you go. So this, please keep in mind that we are no longer using both CPU nodes, just one, due to hardware limitations. So just using one, just think of this, the same testing we did, but just with one CPU node. And we did an apples-to-apples comparison. When we enabled QuickAssist, boom, 100,000 connections per second. For RSA 2K key size, testing as a web server. And reverse proxy, same thing. Just a little lower, just under 100,000 connections per second. So stay tuned for more news on QuickAssist with NGINX.
Native support anytime soon?
Soon, yes. Maybe, we'll see. Just, we're really excited about it. Just stay tuned for it, for sure. Okay. Sorry? Ubuntu Xenial. Yes. So everything's the same, except we're using CPU node 1 only. One CPU node. Pretty cool, right? Big performance. Whoa. Okay, so to summarize, we went over four performance tips. First tip, deploy 2 NGINX instances, one bound to CPU node 1, one bound to CPU node 0. The second one, we went over additional NGINX configurations that you could add to your configuration to further maximize performance. We went over some Linux sysctl parameter tuning, although it wasn't too effective, but you can go ahead and play around with that if you have time. Setting IRQ affinity using receive side scaling and transmit packet steering to reduce bottleneck when receiving incoming connections. And of course, QuickAssist. Stay tuned for more news on NGINX with QuickAssist. If you want to looking to use a hardware load balancer that is much cheaper and super high performant. There will be an appendix for additional information on like the client scripts and the hardware architecture used and all that great stuff. And I think we are done. Thank you very much.
Can I?
Yes.
I've been interrupting, sorry. SO reuse mode that you mentioned, right?
Right.
That I've tested it with and without, and I've not seen a lot of performance difference. Can you talk a little bit about what is it that what kind of load should we be running to really see that effect? Because I see, documentation aside, I'm trying to figure out how that really gets used, because there are some scenarios where I think it makes sense and there are other scenarios that it doesn't. So perhaps in my testing, I've not been able to figure out how that
So the way I was testing it is, for example, accept mutex on. So if you enable accept mutex, right, where only one socket listener is by turn talks to a worker process versus using reuse port, it's significant. Do you agree with me?
Yes, it is. That's how it's supposed to be, but I was just wondering.
That's not, and you're not seeing that?
I'm not seeing it that way. That's why I was asking that question. Is it the connection churn that's supposed to happen that makes that difference, or what is it? That's what I was trying to figure out. Is that what the payload should be?
How many worker processes were you using?
20.
20. Okay, so yes, the more worker processes you use, the more significant the performance will be, like improvements.
Yeah.
So 20, you should see it. Did you reproduce what I had here?
No, in my test, the performance difference wasn't significant enough to make it statistically any difference, and that's why I was trying to figure out maybe something that I'm not doing.
So try it with this and see what happens. I can't look into your config.
But this is something
Yeah, this is something I have seen. I will add a graph in the appendix that shows that. So, yeah. Any other questions? NIC TLS offloading. Instead of, it's, well, you mean TLS? No, we did not. No.
In your configuration file, you mentioned you given an IP address. It's possible to directly use a Unix socket instead of a TCP socket for performance reasons. Like in Linux, you have the possibility to switch between TCP and Unix sockets. In my experience, I would see performance boosts because of that.
I don't think we can set TCP.
Well, the testing was done with NGINX and reverse proxy, so about a physical config server. So you could use the Unix socket in that case. But just thinking of it conceptually, if you use the Unix socket versus going to the network code, but you're restricted to Unix.
All right. Thank you.